We've got one last topic to look at in this chapter: tides. Tides are the gradual up and down movement of the ocean water over the course of a day. Along most coastlines, we see 2 high tides and 2 low tides every day. For as long as people have been watching the tides, it seemed obvious that tides are somehow connected to the moon. But it wasn't until there was a law of universal gravity that anybody could make sense of what that connection was. To understand tides, we start by considering the moon's gravity pulling on the Earth. This causes the Earth to accelerate towards the moon, making the Earth wobble back and forth in its orbit as the moon moves around us each month. However, remember that gravity depends on distance, so not all parts of the Earth feel the same pull from the moon. The side of the Earth facing the moon feels a stronger pull than the side facing away from the moon, simply because the side facing towards the moon is closer to it. Have a look at this diagram. All of the Earth is pulled towards the moon, but since different parts of the Earth are being pulled by different amounts, the forces try to stretch the Earth into a football shape. The side closest to the moon feels a stronger pull, so it stretches towards the moon. The opposite side feels a weaker pull, so it lags behind, effectively stretching away from the moon. So the tidal force we feel from the moon isn't just caused by the moon's gravity. It's caused by the fact that different parts of the Earth feel different gravitational pulls from the moon. These different pulls try to stretch the Earth out. That's what this diagram is showing. So, what does this have to do with the oceans? The tidal force pulls on both rock and water. However, the water can respond to this force much more easily than rock. It's simply that much more fluid. The rocks of the Earth do flex a little due to tides, just not very much. Since water responds to the tidal force more quickly than rock does, it tends to flow into the tidal bulges facing towards and away from the moon. This creates 2 locations with high tide, one facing towards the moon and one facing away. Since the Earth is spinning, we're carried through both of these tidal bulges each day. That's why we have 2 high tides every day. What I've just described is the simple picture of how tides work, and it works fairly well in the deep ocean. However, the picture becomes much more complex because the Earth has coastlines. The shapes of coastlines and sea bottoms funnel water into specific locations, delay the motion of water into the tidal bulges, and generally make the size and timing of tides much harder to predict than you would suspect from the model we've just looked at. In fact, if you want to predict tides in a given location, the best way to do that is to look at the historical record and see what the tides have been for a given phase and location of the moon in the past. This illustrates an important point about science. Often, even when a model gives a good description of a basic physical process, like tides, it will still have to be modified to match the specific details we observe, simply because the world is so complex. This means that we have to treat the model as a starting point for understanding rather than the complete answer. So far, we've seen that the moon generates 2 high tides on the Earth. However, the sun also creates 2 high tides. The sun's tides are a little more than 1/3 as high as the ones caused by the moon, but they do have a noticeable effect because they change the size of the tides generated by the moon. When the sun and the moon are lined up, we get what is called a spring tide. In a spring tide, the high tide is higher than we would get just from the moon, and the low tide is lower. This happens because the sun is trying to make a high tide on top of the moon's high tides, and a low tide on top of the moon's low tides. So in a spring tide, the difference between high and low tides is especially large. Notice that this just depends on the location of the sun and moon. It doesn't have anything to do with the season, spring. When the sun's tides are at 90 degrees to the moon's tides, we have what is called a neap tide. Here, the sun is trying to create a high tide where the moon is trying to create a low tide, and vice versa. Since they're working against each other, the high tides aren't very high, and the low tides aren't very low. And in other words, the difference between high and low tides is small at this time. Let's see if you got the connection between moon phase and tides. One time we see a spring tide is at new moon, as shown in this diagram. The moon is trying to raise tides on the right and left sides of the Earth. The sun is also trying to raise tides on the left and right sides. Since they're both creating high tides at the same locations, we have a spring tide with a very high tide and a low tide. A full moon should look the same, except that the moon is on the other side of the Earth, so it will have a spring tide as well. Thus, the answer is that both new and full moons give spring tides. So, what happens at first and third quarter? This diagram represents a third quarter moon. Here, the moon is raising high tides at the top and bottom of the diagram. Notice that this isn't the North and South poles. We're looking down on the North Pole here. In fact, these are the sunrise and sunset locations on the Earth. The sun is still trying to produce high tides on the right and left sides. Here the moon's high tides are in one place and the sun's are 90 degrees away from them. So the two are working against each other and we have a neap tide. The difference between high and low tides isn't as dramatic here as in the case of spring tide. The first quarter moon diagram will look the same as this, except that the moon will appear below the Earth rather than above it. So we see here that there is a direct connection between the phase of the moon and the size of the tides. This is a very strong correlation, and if you have some experience with tide charts, you can often get a pretty good idea of what the moon's phase is just from looking at the tides, and vice versa.
Now you should fill in this table describing spring and neap tides, including what happens to the low and high tides at each, and what the moon phase has to be.
If moving water around in the Earth's oceans was the only thing tides did, it wouldn't be very interesting astronomically. However, tides have longer-term effects that can be very important for planets and moons around the solar system. The reason for this is that tides cause friction. Tides make the rock of the Earth shift up and down, and the oceans move back and forth on the surface. All of this squeezing and sloshing generates heat through friction. As we saw when we first started looking at energy, friction is a way of turning kinetic energy into heat. So whenever we see friction, it probably means that some moving body is slowing down. In the case of the Earth, that slowdown is coming from its spin. Over time, the Earth's spin slows down. We actually see evidence of this in the geologic record. Fossil beds that have daily and annual cycles show more days per year hundreds of millions of years ago. This indicates that the Earth was spinning faster in the past than it does now. We can also measure this slowdown today using very accurate clocks to time the Earth's rotation. But the moon is much smaller than the Earth, so it should respond to this sort of tidal slowing more quickly. In fact, the moon has slowed down so much that it always keeps the same side towards the Earth. We already saw this when we looked at the moon's motion back in Chapter 2. Think about what this means from the point of view of tides. Tidal friction happens on the Earth because the tidal bulges change position. Both bulges go all the way around the Earth as we spin every day, so the ground flexes up and down twice each day. But on the moon, the tidal bulges stay in one place, one on the side facing the Earth and the other on the side facing away. Since the bulges don't move, there isn't any friction, and so the moon's spin doesn't change. So the fact that the moon keeps the same face towards the Earth isn't an accident. It's a direct result of the tidal force exerted by the Earth on the moon. Our moon isn't alone in this. Almost all of the moons in our solar system do the same thing. They keep the same face towards their planet because of the effects of tides. Tidal evolution has one more important effect on the Earth-Moon system. We've already seen that tides are slowing the Earth's spin down. However, this itself can have an effect on the Moon's orbit. The Moon's orbit is changing because the Earth's spin causes the tidal bulge to be pulled a little ahead of the line between the Earth and Moon. As a result, the bulge on the side of the Earth nearest the Moon tends to drag the Moon forward in its orbit, boosting it into a higher orbit. So slowly over time, the Moon's orbit is getting farther away from the Earth. This effect can be measured directly by bouncing lasers off of mirrors placed on the Moon's surface during the Apollo program. We can use this to get very accurate measurements of the Moon's distance. As we'll see later, this has important implications for the Moon's history. It suggests that the Moon probably formed very close to the Earth, possibly just a few Earth radii away instead of the 60 Earth radii it is now. Tides have caused it to slowly drift farther away over the past several billion years. This same process is happening to moons all over the solar system, causing them to drift farther or in a few cases closer to their planets over time. Lastly, we should look at what happens to the heat that is released in tidal friction. In the case of the Earth-Moon system, this friction is too small to matter much. Other heat sources dominate in the Earth. The slow spin means that the Moon's tidal bulge hardly moves, though it does get slightly larger and smaller as the Moon's distance from the Earth changes due to its elliptical orbit. However, some other moon systems get more heat from tides. In particular, the moons of the outer solar system planets often have a lot of tidal heating. These are systems in which many moons orbit the same planet, tugging on each other as well as feeling the tidal pull of the planet itself. As a result, tidal evolution is very strong in these systems, and there's a lot of heat generated this way. The poster child for this is Io, the innermost large moon of Jupiter. We're looking at the surface of Io here. Almost everything you're seeing on the surface of this moon is a recent volcanic feature of one sort or another. Io is the most volcanic world in the solar system, and the bulk of the heat generated comes from tides. In fact, just before the first spacecraft got close-up pictures of Io, a group of scientists predicted that it would be volcanic simply because of all the tidal friction it was experiencing. They were able to predict that Io would look like this because of their understanding of gravity and tides.